Alright, in this video here, we're going to be talking about the graphs of the tangent and cotangent functions. Alright, so the graphs of these two functions, just like this, the graphs of sine and cosine, if you didn't watch the videos that I did on graphing those two functions, the graphs of sine and cosine are pretty similar to each other with, a couple, well, really one little exception as far as like their starting point, but the graphs look similar. Well, the graphs of tangent and cotangent also look kind of similar to each other, but there's definitely a couple of differences that you need to be aware of with the graphs of these two functions. Alright, so I put up here the unit circle. Alright, I'm going to be drawing these graphs based on the points on the unit circle. So, I didn't put up every point on the unit circle, so that would have just made that thing too cluttered and like just too much information up there. So I just put up the major points on the x and y axis. So 0, pi over 2 pi, 3 pi over 2, and then back to 2 pi. That'll give us enough information to be able to figure out what the graphs of tangent and cotangent look like. Alright, so the graph of y equals tangent of x. Well, go back to the unit circle and the definition of the tangent function in terms of your terminal point on the unit circle. Right? The definition of the tangent function is tangent of t equals y over x. Right? So if I want to find the tangent of 0, the terminal point for 0 is 1 comma 0. Right? So the y is 0 over the x of 1, so it's 0 over 1, which would be 0. Right, so that's the definition of the tangent function in terms of the unit circle, the y-coordinate of your terminal point over the x-coordinate of your terminal point. Now though, since the definition involves that fraction with the x in the denominator, that means that there's going to be times when the tangent function is not defined. Right? It's not going to be defined whenever x is equal to 0. Right? Because I cannot have 0 in the denominator of a fraction. That's not allowed mathematically. That has no definition. It just does not exist. Right? So the key thing for the graph of the tangent function is, well, where does x equal 0? Where am I going to have the function not exist? That's where I'm actually going to get vertical asymptotes. Right? So I did a video about rational functions a while back, actually probably a few videos about rational functions. But one of the things about rational functions, when you have a function that involves a fraction, wherever that denominator equals 0, you get vertical asymptotes. Well, for the tangent function, since it represents a fraction, wherever that denominator equals 0, we're going to have vertical asymptotes. Right, so where does x equal 0? Well, on the unit circle, x equals 0 up here, right, at the point for pi over 2. So at pi over 2, since x equals 0, my tangent function does not exist, so at pi over 2, I'm going to get a vertical asymptote. Right, where else does x equal 0? Well, if I go around to here, at 3 pi over 2, I also have an x-coordinate of 0. So at 3 pi over 2, I'm once again going to have a vertical asymptote for the tangent function. Right, and same for negative values. If I go in the negative direction at negative pi over 2 and negative 3 pi over 2, I'm going to have vertical asymptotes for the tangent graph. Right, so the tangent function is going to have vertical asymptotes at every pi over 2 number. 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on. Right, so every time you have a number that involves a pi over 2, you have a vertical asymptote for the graph of the tangent function, because at all those pi over 2 numbers, that's when your terminal point is on the y-axis, and when your x-coordinate equals 0, and the definition of the tangent function is x is in the denominator, right? So we can't have that 0 in the denominator. That's what leads us to these vertical asymptotes. Right, so that's the key thing for the graph of the tangent and the cotangent function, which we'll get to in a couple minutes, is knowing where those asymptotes are, right? And if you ever forget, because the two of them are not in the same place, right? So for tangent, it's at the pi over 2 numbers. If you forget that, remember the definition of tangent. Tangent is the y-coordinate over the x-coordinate. So wherever my x-coordinate equals 0, which is at the top and the bottom of the unit circle, that's where my function doesn't exist. That's where I get my asymptotes at pi over 2 and 3 pi over 2, and then every other pi over 2. Right? Just like the graphs of the sine and the cosine functions, the graphs of all of the trig functions are periodic. Right? So tangent, the graph is going to be periodic. So if I can figure out what's going on, between either one of these asymptotes, basically I then just repeat that pattern over and over again between each pair of vertical asymptotes, and it just repeats the same shape over and over again. All right, so that's what we're going to have here. All right, so the question then is, well, what's going on in between the asymptotes? Well, what about at 0? Right, when t is equal to 0, my definition is y over x. My y is 0, my x is 1. 0 over 1 equals 0. Right, so when I plug in t equals 0 to the tangent function, I get a value of 0. Right, because I do the y over the x, 0 over 1, which simplifies to equal 0. Right? for pi, right? If I go halfway around the unit circle and I do the tangent of pi, well, once again, the y over the x is going to be 0 over -1. 0 over any non-zero number equals 0. So at pi, I'm also going to be at 0. Right? And like I said, the tangent function is periodic, so at every one of these pi numbers, the tangent function is going to have its x-intercept. Right? The tangent function is going to cross the x-axis at every multiple of pi. So 0, 1 pi, 2 pi, 3 pi, 4 pi, -1 pi, -2 pi, -3 pi. Right? That's where the tangent function is going to hit the x-axis because, you know, every time I hit a pi number, so 1 pi, 2 pi, 3 pi, 4 pi, my y is 0 and my x is not 0. Y over x, 0 over any number, equals 0. All right, so now I know that in the middle between the two asymptotes is where my graph crosses the x-axis. Then the question just is, well, which direction does it go? Does it go from up here and go down, or does it go from the bottom up to the top, each one, or in between each set of asymptotes? All right, and the answer to that is it goes from the bottom up to the top. Right, and just to kind of give you an idea of why that is, and again, this goes back to something I talked about on the video of rational functions and vertical asymptotes, and how to tell on either side of the asymptote, is the graph going to be going up towards infinity or down towards negative infinity? Well, as I approach pi over 2 from the left side, right, so as I'm coming to pi over 2, I'm coming this way along the unit circle. When I do the y over the x, well, both the y and the x, when I'm in that first quadrant, are going to be positive numbers, and so as I approach pi over 2 from the right side, y over x is always going to give me a positive answer, so the graph is going to be going upwards, you know, as I approach pi over 2 from the left side. Right? What about as I approach negative pi over 2 coming from the right side this way? Right? So coming over here. So if I'm going towards negative pi over 2 going this way around the unit circle, I'm in the fourth quadrant where my x is positive but my y is negative. So if I do a negative y over a positive x, it's going to give me a negative result, which means as I approach negative pi over 2 from the left or from the right side here, you know, going this way along the unit circle, I'm going down towards negative infinity. And so my graph for the tangent function looks like that. Right? That's the graph of one period of the tangent function. In between negative pi over 2 and pi over 2, it starts down towards negative infinity. You know, at 0, it goes through the origin there, and then it goes up towards positive infinity as I approach pi over 2. And then it repeats that over and over again forever. So in between every one of these asymptotes, the graph of tangent is down on the left, through the x-axis, and then up on the right. Right? And when it goes through the x-axis, it's at all those multiples of pi. Right? So over here, it's down on the left, it's going to go up through the x-axis at 2 pi, and then it's going to go up to another asymptote. Over here, it's going to be down through the x-axis at negative pi, and then up. Over here, it's going to be up on that side. So there's the graph of several periods of the tangent function. Right, so the key thing to remember for the tangent function, where the asymptotes are, the pi over 2 numbers, right, so negative pi over 2 to pi over 2. That one in the middle is usually the one that we use as like the first period of the tangent function because it goes through the origin, so it's like right in the middle of our graph. Right, so from negative pi over 2 to pi over 2, that's where our asymptotes are, and then we just remember it's down on the left and then curves and goes up on the right. Right, so that's what our graph of the tangent function looks like. Right, for the cotangent function, similar idea, but a little bit different because the definition of tangent, or I'm sorry, the definition of cotangent of t is equal to x over y. Right, remember, cotangent is the reciprocal of tangent. Tangent is y over x. I flip that over for cotangent, which is x over y. Right, so the cotangent function is going to have its vertical asymptotes wherever y is equal to 0. Right, because now we have y in our denominator, and I can't have 0 in the denominator of the fraction. So where does y equal 0? Well, right here when I'm along the x-axis. So at 0, I have y equals 0. So there's a vertical asymptote at 0. When I move over here to pi, I have a y coordinate of 0. Right, so at pi, I have a vertical asymptote. When I go all the way around the circle to 2 pi, I have a y coordinate of 0. All right, so I have a vertical asymptote at 2 pi. And same when I go in the negative direction. If I go negative pi around this way, I end up with a y coordinate of 0 again. So for the cotangent function, the vertical asymptotes are at all the pi numbers, all the multiples of pi. Right, so that's one of the differences between tangent and cotangent. Right, tangent, the asymptotes are at the pi over 2 numbers. Cotangent, the asymptotes are at the pi numbers. right? So all the multiples of pi. And it can be really confusing as far as which one is which. But remember, if you go back to the definition, cotangent is x over y. The vertical asymptotes are where you have 0 in the denominator. So understanding that allows you to piece this together and not have to memorize what the graph looks like, right? So vertical asymptotes is where 0 is in the denominator. Cotangent is x over y. So wherever y equals 0, I've got vertical asymptotes, y equals 0 at 0, pi, 2 pi, 3 pi, 4 pi, and so on. So that gives you where the vertical asymptotes are. Whereas for the tangent function, since it's y over x, the vertical asymptotes are going to be where x equals 0, which is at those pi over 2 numbers. Right? So again, having that understanding of why you have vertical asymptotes is because the denominator equals 0, and then understanding the definitions of these two functions in terms of the unit circle and the terminal points. If you understand those two things, you don't have to memorize these graphs. You can just think about it a little bit and figure out, oh, I know where the asymptotes are now because it's where that denominator equals 0. Right? In my mind, understanding is always better than just memorization. Right? Because memorization goes away, understanding kind of sticks with you. Right? So here we go now. The cotangent function. So we have different asymptotes, right? And then the cotangent function also is going to be going in the opposite direction of the tangent function, right? The tangent function starts low in one of its periods and then goes high. The cotangent function is actually going to go the other way, right? If you think about it, if I'm going towards pi, right? If I'm approaching pi from the left side, I'm going through the second quadrant to get close to pi here, my x is negative and my y is positive. If I do a negative x over a positive y, I'm going to have a negative value. So as I approach pi from the left side, my graph is going to be going downwards. Right? At pi over 2, right, that's where x is 0 and y is 1. If I do 0 over 1, I'm going to have 0 at pi over 2. Right? So for the cotangent function, the x-intercepts are at the pi over 2 numbers. Right? So, and that's another relationship between these two. Now, where the tangent function has its vertical asymptotes, that's where cotangent has the x-intercepts. Where tangent has the x-intercepts, that's where cotangent has the vertical asymptotes. Right? So they switch their asymptotes and intercepts because they're switching which coordinate, x or y, from the unit circle is on top and bottom. Right? And they also switch directions. So tangent goes from the bottom up towards the top. The graph of the cotangent function starts high and then decreases down through its period and finishes low. All right? And then it repeats that same pattern between every set of asymptotes. It's going to start high and go low. Right? And again, you can, if you forget that, you can figure that out by just thinking about, well, as I get close to, as I get close to 0 coming from the right side. So if I'm coming from 0 this way, I have a positive x and a positive y. Positive over positive is positive. So as I approach 0 from the positive side, I'm going up towards positive infinity. Hopefully that makes sense the way I'm describing that. But if you just pick some points close to the graph and the x and the y and just plug the numbers in, if it comes out to a positive number, you're going towards positive infinity. If it comes out to a negative number, you're going towards negative infinity. So that gives you an idea of which direction you're going. And again, we did something similar when I did the video on rational functions and figuring out what's going on either side of your vertical asymptotes. We did a really similar thing there, which is why I'm not spending too much time talking about it. If you don't know what I'm talking about, go find the video that I did on rational functions and vertical asymptotes, and it describes in more detail how to tell whether the graph is going up or down on each side of the asymptote. Right? Basically, just plug in some numbers that are close to this value and see what happens. All right, so there's our graphs of tangent and cotangent. Similar, right? They have similar looks to them, but they're definitely different. Right? They have different vertical asymptotes, they have different x-intercepts, and the x-intercepts and asymptotes are switched from one to the other. Right? So if you know what the graph of tangent looks like, you can piece together the graph of cotangent just by switching stuff around. All right, so everywhere that this graph has the vertical asymptotes, that's where I'm going to put the x-intercepts for this graph. Everywhere this graph has the x-intercepts, that's where I put the asymptotes for that graph. And then this one goes from low to high. Cotangent is the opposite. It goes from high to low. All right, so there's your graphs of tangent and cotangent. Now, the rules for transformations of graphs also apply to these. So you can do vertical stretches and shrinks and, vertical shifts up and down, horizontal shifts left and right, horizontal stretches and shrinks. All right, so all those other rules for graphing functions apply for doing the transformation, just like with any other type of function. Right? I'm not going to spend any time talking about that because you usually don't see those types of problems very often. But it is important to have just a basic idea of what the graphs of the tangent and the cotangent function looks like, which, feast your eyes, here it is.